The focus of this video is understanding the normal curve, standard deviations, and the mean in relation to the normal curve, and how z-scores are calculated and used. When data are perfectly normal, they will fall in a shape known as the normal curve or the bell curve. This is also sometimes called the normal distribution. For this lecture, we're going to presume that the data are all normally distributed. There are a few notable characteristics of the normal curve, many of which are clear when we're looking at a depiction of the normal curve. The first is that the mean, the median, and the mode are at the center of the normal curve. The tails of the curve are also theoretically asymptotic, and the two halves of the normal curve to the left and to the right of the mean, median, mode central line are symmetrical. The normal distribution curve has an x and y axis. The x-axis corresponds to the raw scores. It will also correspond to the z-scores. We'll look at that in a little bit. The y-axis corresponds to the frequency with which each raw score occurred. Essentially, therefore, the normal distribution curve is a histogram that's a representation of quantitative data frequencies that has been smoothed over. Here I've sketched in some bars to show you what a histogram underlying this normal distribution would look like. Quantitative data are often summarized using the mean and the standard deviation. To learn more about how a standard deviation is calculated, you should view a different video. Here we'll talk about how the mean and standard deviation relate to the normal distribution curve. Typically, when you see the normal distribution curve, you'll see vertical bars to the left and to the right of the mean line. These represent movements from the mean in standard deviations. Remember that theoretically the graph can keep going. However, you'll typically see the graph going from -3 to 3. That's movement of 3 lines to the left of the mean and 3 lines to the right of the mean. The lines correspond to movements in standard deviations below the mean to the left and above the mean to the right. This means that the raw scores are being shown based on how many standard deviations they are from the mean. Let's say we have a sample with a mean of 10 and a standard deviation of 2. We can start to fill in the normal distribution curve by putting the mean at the center of our graph. We then move in standard deviations above the mean and below the mean. To be 1 standard deviation above the mean corresponds to the mean plus 1 standard deviation, which is 2. Being 1 standard deviation above the mean, then, corresponds to a raw score of 12 in this scenario. Being 2 standard deviations above the mean corresponds to a raw score of 14. Being 3 standard deviations above the mean corresponds to a raw score of 16. If we are 1 standard deviation below the mean, that's the mean minus a standard deviation. This corresponds to a raw score of 8. 2 standard deviations below the mean in this example would be a 6, and 3 standard deviations below the mean would correspond to a raw score of 4. When we look at how many standard deviations a raw score is from the mean, we call this a z-score. A z-score simply means where is the raw score in relation to the mean if we're moving in standard deviation units. Another way of saying this is that the z-score corresponds to the bar location of the raw score. If a raw score is 10, its z-score is 0. That's because a raw score of 10 is exactly at the mean, since we already identified that the mean was 10, and we can see clearly that this is the bar in the very center of the graph, or the vertical line at the very center of the graph. A raw score of 12 is exactly 1 standard deviation above the mean, or to the right of the mean, so that corresponds to a z-score of 1. 14 is 2 standard deviations above the mean, so it has a z-score of 2, and 16 is 3 standard deviations above the mean, so it has a z-score of 3. Notice that when we move to the right of the central bar, we see positive z-scores that are increasing. If we look to the left of the mean, median, mode line at the center, we're going to be decreasing in z. A score of 8 corresponds to being 1 standard deviation below the mean, or to the left of the mean, because 8 is lower than 10. A 6 is 2 standard deviations below the mean, and a 4 is 3 standard deviations below the mean. So a raw score of 8 corresponds to a z-score of -1, which means 1 standard deviation below the mean. A raw score of 6 corresponds to a z-score of -2 because 6 is 2 standard deviations below the mean, and a raw score of 4 corresponds to a z-score of -3 because it's 3 standard deviations below the mean. Therefore, z-scores simply tell us how many standard deviations above or below the mean each raw score is. If a raw score is higher than the mean, it will have a positive z-score. If a raw score is lower than the mean, it'll have a negative z-score. And if a raw score is identical to the mean, it'll have a z-score of 0. Let's take a moment to focus on what this tells us visually. Notice that the sections that are 1 standard deviation below the mean to the mean, and from 1 standard deviation above the mean to the mean, are quite large. We have a big proportion of our graph that's from a z-score of -1 to a z-score of +1. In fact, if our data are perfectly normal, this will correspond to a little bit over 68% of the raw scores. If you look at our picture here, I've highlighted this location or these 2 locations in green to show you how clearly this looks like it's a large section of our graph. However, as we move further away from the mean, such as going from 1 standard deviation to 2 standard deviations above the mean, or from 1 standard deviation below to 2 standard deviations below the mean, the sections of the graph are getting smaller. This is because of the sloping nature of the curve, that we're moving towards those asymptotic tails. And if we look even further out, going from 2 to 3 standard deviations above the mean and 2 to 3 standard deviations below the mean, we can very clearly see how small the areas under the graph, or the area under the graph, is becoming. If you look at the area out under the tails, which I've highlighted here in a fuchsia color, you'll see that a very small portion of the graph is colored in. When we're looking at areas getting closer and closer to the mean, the size of the shaded portions is getting larger and larger. The area of the curve corresponds to the probability of scores. Therefore, scores closer to the mean, such as those within 1 standard deviation above the mean and 1 standard deviation below the mean, here noted in green, are far more likely to occur or to be selected randomly than scores that are further from the mean, such as those that I've highlighted in fuchsia that are 2 to 3 standard deviations above the mean or between 2 and 3 standard deviations below the mean. Scores that are closer to the mean are more likely to occur and are thus more likely to be randomly selected when data are normally distributed than are scores that are further from the mean. Let's consider a quick example. Let's say I wanted to know which score was more likely to be randomly selected from this distribution of data, a raw score of an 11 or a raw score of 15. I've noted them here in my graph. You can see that those are both in the positive side of the graph because they are to the right of the mean line. However, they're not equally likely to be selected. The raw score of 11 has a higher probability of being randomly selected than does a raw score of 15. This is because the raw score of 11 is closer to the mean and thus corresponds to a taller part of the graph than does a raw score of 15. Whichever raw score is closest to the mean is the one that is more likely to be randomly selected. That's because as scores become closer to the mean, they are presumed to be more likely to occur. And whatever is more likely to occur is more likely to be randomly selected. Similarly, whichever z-score is closer to 0 has the greater likelihood of occurring and thus the greater probability of being selected at random. The z-score that has the highest chance of random selection is a z-score of 0. The raw score with the highest chance of being selected is a raw score of 10, because both of these correspond to the center of the graph. As we move closer to the center, scores become more likely and thus more probable when we're looking at random selection. You might have noticed that the raw score of 11 is directly between the raw scores of 10 and 12. Because 10 and 12 correspond to z-scores of 0 and 1 respectively, the score of 11 falling directly between them will correspond to a z-score of 0.5. We can see that its location on the graph aligns. The raw score of 15 falls directly between the raw scores of 14 and 16, which correspond to z-scores of 2 and 3. Because it's dead center between those raw scores, it's also dead center between those two z-scores, and thus a raw score of 15 has a z-score of 2.5. We already noted that the score of 11 is more likely to be selected at random because it has more occurrences. That's because it's closer to the mean. You'll also note here that it has the smaller z-score in absolute value relative to the raw score of 15, which had the higher z-score. When we're trying to decide which raw score is more common or more likely to be randomly selected, it will always be the one that is closer to the mean. Another way of saying this is that it will always be the score that has the smaller z-score in absolute value. However, raw scores that are equally distanced below and above the mean are equally likely to occur. For example, a raw score of 9 has a z-score of negative 0.5. A raw score of 11 in this example has a z-score of 0.5. Because their z-scores are the same in absolute value, these two raw scores are equally likely to be randomly selected from the distribution. Let's take a look at this with another example. We'll use height in inches. Presume that the mean height in inches for a woman is 63.8 inches, and that the standard deviation for a woman's height is 2.8 inches. Here we have a blank normal distribution showing what each bar location represents. The mean at the center, and the mean plus 1 standard deviation to the right, the mean plus 2 standard deviations further to the right, and the mean plus 3 standard deviations as the last marker to the right. We also move to the left in standard deviations, so we have the mean minus a standard deviation, the mean minus 2 standard deviations, and then finally the mean minus 3 standard deviations. Pause here and fill in the raw scores that will correspond to each of these bar locations. That means put a raw score below each of the vertical lines you see in the graph. To get started, let's put the mean at the center corresponding to the mean line. Now find what each of the other vertical bars will be, and then press play to check your answers. Take a moment to look at the answers here. As we move from the mean of 63.8 inches to the right, we see raw scores of 66.6, 69.4, and 72.2. As we move to the left, descending from the mean, we see decreasing raw scores going to 61.0, 58.2, and 55.4. Keeping this in mind, try to answer the following questions. Number 1. What is the z-score when the raw score is 61.0? Number 2. What is the raw score when z equals 2? In the first one, we want to know what the z-score is when the raw score is 61.0. I can see that 61.0 is 1 standard deviation below the mean. That means it has a z-score of negative 1 because it's one movement in standard deviations below the mean. For the second question, what is the raw score when z equals 2? Well, I need to find the z-score that is, or the raw score that corresponds to being 2 standard deviations above the mean. If we're 2 standard deviations above the mean, the corresponding raw score is 69.4. So when you have a z-score of 2, in this example, your raw score is 69.4. Let's try a new set of questions. Which of each set of z-scores is more likely to be randomly selected? Let's start with a z-score of negative 1 versus a z-score of 2. Which is more likely to be randomly selected? You should have picked a z-score of negative 1 because a z-score of negative 1 is closer to the mean, or it's closer to being 0. 0, the z-score of 0, is the one that's the most likely to be randomly selected. You can see that the location of a z of negative 1 has a taller corresponding location in the curve compared to that corresponding to a z-score of 2. Let's try another. Which z-score is more likely to be randomly selected? A z of negative 1 or a z of 1? For this one, you should have found that a z of negative 1 and a z of 1 are equally likely to be selected because they're equally far from that mean z of 0. Notice that the height of these two locations in our sketch is the same, that these two locations are equally likely to occur because they're equally close to the mean. Let's try it again, but this time with raw scores. Remember that raw scores and z-scores correspond to one another. Which of each set of raw scores is more likely to be randomly selected? a raw score of 63.8, or a raw score of 58.2. You should select a raw score of 63.8. This corresponds to the tallest part of the graph. In fact, this is the exact mean, and the mean is more likely to be randomly selected, theoretically, than any other number in a normally distributed data set. The score of 58.2 corresponds to a z-score of -2. That means it's 2 standard deviations below the mean, and you can see that the height of that location on the graph is much lower than the height of the mean or center of the graph. Let's try one more. Which raw score is more likely to be randomly selected? A raw score of 55.4 or a raw score of 72.2? You should have noticed that these two scores are equally likely to occur because they are equally far from the mean, and they are of equal height on the graph. A score that is 3 standard deviations below the mean and a score that is 3 standard deviations above the mean have an equal chance of being selected at random. Pause here and try a quick practice. Remember that you don't need to know the raw score or the standard deviation to know which z-score is more likely to be randomly selected. The z-score that is closer to the mean, or closer to a z of 0, is always the one that is more likely to be selected at random theoretically. Try these 5. For each set of z-scores, choose which one is more likely to be randomly selected. Number 1, z of 2 or a z of -2. Number 2, a z of -1 or a z of -1.5. Number 3, a z of -3 or a z of 2. Number 4, a z of 0 or a z of 1. And finally, number 5, a z of 0 or a z of 0.5. Pause here, get your answers, and then hit play to see the results. For number 1, you should have noted that 2 and -2 are equally likely to be selected at random because they have the same absolute value. That means they'll be equally far from 0. In number 2, you should have noted that -1, which is closer in absolute value, is closer to 0 because its absolute value is lower, has a greater chance of being randomly selected than a -1.5. For 3, you should have noted that 2 has the smaller absolute value and thus is more likely to be selected than a -3. For number 4, you should have selected 0, and for number 5, you should have selected 0. Remember, when the z-score is 0, that means we are at the mean, and the score at the mean is the most likely to be randomly selected. That means a z-score of 0 is also the most likely to be randomly selected.